story of communication from classical to quantum and what. We welcome Dr. Manik Banik. On the behalf of society and all of you present here, and we'd like to welcome.
So first I'd like to thank Ravi Kiran Adi and his and their of the it is a beautiful opportunity to continue our research work and so today I'll talk, let me present my we in the communication era. Every social media, whatever we used, Facebook, WhatsApp, these are nothing but some communication medium. So what is the simplest communication medium? So this is the plan of my talk. I'm not reading these things. Let's go into details in talks and see. So what is the simplest communication thing? Simplest communication things that we can think as a mobile or telephone. Why I call it simplest? Because it's but in Facebook you can have only sender, many people. These are much complex. Our study this physics this technological development of phone, rather we will respect it. Science paper in mathematical theory of communication, Claude Shannon actually proved two theorem. One is called source coding theorem, and another is the channel coding theorem. So source coding theorem today we will not discuss, not because source coding theorem is not that much relevant for our communication. In our computer we use some language nowadays. Okay, I zip some file, means not Shannon's source coding some theoretically, and this is the functional form is given. The simple information theoretic meaning to that particular. So this model of function we can think as a sender. Sender encode his or her. Then some channel what not exact message come to this receiver. It got since the channel is a noisy one. Most of the practical scenario, the channels are noisy one. So now Shannon's channel coding question was how to mathematically model such a channel. So Shannon had pointed out that this information source we can think as a random variable x, where x follows some probability distribution, and the receiver decodes some obtains some y, a different message or different symbol y distribution. What is this channel? Channel is this channel action. How we can understand? Channel means receiving this Y, how good we can guess the original message X. So channel is nothing but a stochastic process from this input probability distribution to the output probability distribution. So what is our next question? Our next question is, if we had some noisy channel, how good this noisy channel is for transferring some information? And Shannon gives the answer, Shannon's channel coding theorem. It tells us that we have to calculate this particular quantity, this maximization of this particular quantity, this IISER, it is called mutual information. So channel capacity is maximization of this mutual information between X, input variable, and output variable, which is defined by Hx, Shannon entropy of input variable minus conditional Shannon entropy of Hx given Y. You look into this formula, this particular formula resembles very like with this entropy what we achieve, we see in thermodynamics, but now it has an information theoretic meaning. And this maximization we have to do over the all input probability distribution. Now, physically we can consider this kind of scenario. We have a particular channel and the sender and receiver, and sender receiver sends some information. Now, how the sender and receiver using this channel, sender sending this information one by one, but using many times. So this is one shot use, but many times. Another scenario we can consider that we have identical copies of the same channel and we put them parallel. And on these parallel copies, we use a global, on this all this arm, we use a global encoding function and some global decoding function. Now we can ask this kind of question that are these two different ways of using this channel similar or different? Channel coding theorem actually establishes that these are same. Whether you use many copies of channel parallelly or same channel many times, you will get the same capacity. In information theory, it is also called the channel capacity, or in other words, mutual information, maximization of mutual information. This is an additive quantity. Okay. And this is channel coding theorem. And as I have said, there is source coding theorem, which gives the ultimate theoretical limit of compressing some data. And where we compress this data, we use different kind of device: magnetic tape, CD, DVD disc, semiconductor, or more modern cloud storage. But all these devices, from a physics point of view, they are classical in the sense that state of this system where we store the information, their state is fixed state, deterministic state. Now we'll move to quantum world. Quantum world, the states are not like as we think classically. There are much more peculiar things. So there are some famous quotation, probably you all have heard about quantum mechanics. So I'm not going to in details of that. But what is quantum mechanics? It's very peculiar. Start with some mathematical postulate. Says that a system is associated with some inverse space. State is described by density operator. What is the notion of state in classical physics? In classical physics, Newtonian physics, is nothing but a point in phase space. And if in statistical mechanics, state is nothing but a probability distribution on phase space. And this partition function. Now, depending on the scenario, this partition function can be different kind of canonical, gram-canonical, or microcanonical. But in quantum mechanics, the state is in quantum mechanics, the notion of state is given by density operator acting on the what is density operator? It is unitary or more generally some possibility completely composite system are described by tensor product system. Tensor product or component system. Now, this here, this is generalization. Once we take this, what we have studied in our textbook, evolution is given by human. Surface quantum mechanics, there are lots of peculiar scenarios, like heard of this Schrodinger cat paradox. dead or alive to be superposition of dead and alive. Look, the superposition. So, look, the superposition means it is not that cat is either live or alive or dead. It is and at the same time it is dead and alive. So it is very difficult to think how to think of this kind of situation. Means two opposing property, it coexists in superposition. So this is peculiar. Of course, so far scientists cannot obtain this kind of superposition state for macroscopic observable like cat or human, but for microscopic observable it is possible. And in our information theory, our aim is to use of this peculiarity from some information theoretic task. Okay. Another peculiar feature of quantum mechanics is called quantum entanglement. So we can prepare two particles and we correlate them in a peculiar way. And now we put one particle here at IISER Thiruvananthapuram and another particle far apart. Still the correlation lies in this entangled particle, and this correlation has no classical analog. Of course, we have to be very careful. Using that correlation, we cannot send any faster than light information. It is not possible. It is prohibited. But some peculiarity we can achieve. So that is one of the aiming quantum information theory. What kind of peculiar work that is possible in quantum world, which is not possible in its classical counterpart, means classical physics. So we can discuss one particular small experiment. This is called a beam splitter. If you send some photon here, it has 50% chance that this photon will be reflected and 50% chance it will be got transmitted. So now this is the experimental scenario. There is a beam splitter. You send the photon. It is 50-50 beam splitter. So if you send, let's say 10,000 photon, 5,000 will go there, 5,000 will go in this horizontal line, 5,000 to vertical. Now these are perfect mirror. Once this photon comes here, it will got deflected here. So 5,000 photon is coming, again going to a second beam splitter, and this beam splitter is again a 50-50 beam splitter. So from here it will go 50% chance it will transmitted, 50% chance it will reflect. So among these 5,000, 2,500 should be collected here. 2,500 should be collected here. Similarly, from this other 5,000 coming in this path, here also 50% should go here and 50% should go there. So if we send, let's say 10,000 photon, our classical intuition say almost 5,000 should be collected here and 5,000 should be collected in this detector. But if we do this experiment in lab, we will find that all the photons will be collected here. No photon will be collected here. So we cannot explain this phenomena using our classical reasoning. We have to consider this kind of scenario, that photon or light at the same time it is particle as well as it is wave. It is called wave particle duality. And there are lots of other peculiarities are there here, delayed choice experiment in the same scenario, but we are not going to that. This I am trying to say, these are the peculiarity of quantum mechanics. Using our classical reasoning, classical logic, we cannot explain this phenomenon. And quantum superposition, if we accept this quantum superposition, then we have a good explanation to this kind of experimental phenomenon, empirical phenomena. Okay, now in this quantum world, what is a communication channel? Okay, in classical world we have discussed this communication channel. You can mathematically model some stochastics map from input probability distribution to output probability distribution. In quantum world, our input system are modeled by some Hilbert space, output are some other Hilbert space H2, and this action of a channel we can think as some completely positive trace preserving map. Now what is this completely positive trace preserving map? So it is input to output system. You can think it as, you take another system, rho is the system for input, and this is the n rho, this channel action, completely positive trace preserving map. You can think it as, okay, take this system and another ancilla system. So system and some part, environmental part. On this total system, some joint unitary action is applying, and then we trace out the environmental part. Then the action is same as this channel. So this channel has particular unitary representation. Also, this channel has some Klaus representation, which is given by this operator sum representation, where these operators are from input to output inverse space, and they satisfy some particular completeness relation. Now, this Klaus representation, this particular representation is also called Sudarshan-Klaus representation, because IISER Sudarshan, one of the most prominent scientists from India, he also independently obtained this similar expression or similar representation. Okay. For example, if we consider the simplest quantum system, that is a two-dimensional quantum system, C2, means you can think as polarization, spin-half system, any quantum system with 2 degrees of freedom, 2 levels. Means if you consider a harmonic oscillator, if you only super select ground state and excited state and neglect all other states, then these two together is a 2-level quantum system. You can consider it as a C2, means qubit system. So for this qubit system, the state space has a beautiful geometric picture. All the density matrix, they are isomorphic to a unit sphere in R3 centered at origin. Now, if we consider compare the same things with our classical 2-level quantum system, this classical state space will be a line passing through this diagonal. So classical, it has only 2 extreme points, a line, but now quantum state space is much richer. It is a sphere. All points in this sphere are valid quantum state. In classical world, it is only line. Now, what is the action of a channel? An action of a channel will map this unit sphere into some ellipsoid inscribed within this sphere. So this is a particular example of channel, and this has Schumacher-Westmoreland channel. So particular purpose they have discussed this channel. Most general action of a qubit channel you can think is like that. This is nothing but a shifted ellipsoid, equation of a shifted ellipsoid. Okay. Now we can ask this question: if we have a quantum channel CPTP map, for what reason we can use this channel? Okay, we can use this channel to transfer some classical information. How? We have some classical index X, we encode this in a quantum state rho X, then the channel action is this curly N, and this receiver obtains some different state N rho X, and on this obtained state, this receiver performs some measurement and try to decode the information X. And if we interested in this kind of task, then the quantity of interest will be classical capacity of a quantum channel. A quantum channel can also be used for private information or private capacity, transferring classical information privately. Like in your Facebook or if you use WhatsApp, it is written that all this information are encrypted. No one can decrypt this data. Yes, it is correct, up to the constraint that our computational power is limited. So in classical world, any security is coming from the assumption that our computational power is limited. Any security protocol underlying in classical process is the security protocol. The basic feature is this RSA protocol, reverse Samir and Edelman protocol. This is based on a very simple principle that if I give you a 2 prime number, you can immediately find their product, but the other way problem is difficult. So the security in classical world comes from the fact that we have some mathematical problem which is easy in one direction, on the other direction it is very hard. But if we have a very high speed computing power, then our security will be breakdown, will not anymore guaranteed. And actually, there is a computer scientist, Peter Shor. He actually established that if we have quantum computer, then we have a very easy, very fast factoring algorithm, and using this quantum computer, we can immediately factor this large number, and our security will be breakdown. And since we are almost very close to get a quantum computer, still there are debate underlying that, then we have to look for some alternative method of secure communication. And quantum mechanics, in one hand, it takes the security from us, classical security, but it gives another security, that is quantum security. And this quantum security is not based on computational complexity. It is based on some physical principle. Like there are, if you believe that our nature is like that, you cannot send faster than, or you cannot send communication instantaneously, then some security can be assured. So in quantum world, the security is assured from some physical principle. And anybody, any of the student, if you are interested, I find that in our institute also, in mathematics departments, some courses offered on this classical cryptography thing. So if anyone of you is interested, you can take this course. Okay, and another thing we can use, so a quantum channel we can use for sending classical information, then the quantity of interest will be classical capacity. We may want to use it for sending classical information but privately, then the quantity of interest will be private capacity, and we can also be interested to send the quantum information. Then the quantity of interest will be called quantum capacity. What is meant by that? This quantum information. Let us give you one example. This is one particular communication task, quantum communication task called quantum teleportation. What is this? So there are again two parties. One is sender and one is receiver. So Alice is the sender and she has some unknown qubit state. Why I call unknown is Alice is given some qubit state phi1. What is the value of A and B? She doesn't know. And there is a very fundamental result in quantum theory, quantum information theory, very basic. Means it requires 2 or 3 lines mathematics to prove that particular theorem. It is called no cloning theorem. The proof is the result is by Uters and Zurek. It tells us that given an unknown quantum state, single copies of this unknown state, you cannot know the state perfectly. So the state is unknown and Alice cannot, since it is only one copy, she cannot know the state. Now the task is, she needs to prepare the same state at Bob's laboratory, which is specially separated from Alice, without sending the particle itself. But the restriction is means she cannot physically send her system to Bob. Means one thing she can do, she take this particle and send it directly to Bob, but that is not allowed. Means you can consider this due to this lockdown, all this post is now closed. She cannot do it. But there is some communication, means they have already phone line that they can use, and they have this peculiar entangled state which is pre-shared among them. Now using this entanglement, there are some simple protocol. One can show that this unknown state can be actually re-prepared at Bob's laboratory. Exactly. So quantum teleportation established that there are some tasks which is impossible in classical world but can perfectly done in quantum world. So there are some steps. I am not going to the details into the teleportation step, and this is the pictorially I am showing this teleportation. So this source, there are entangled particle. There are some unknown particle to Alice. On this unknown particle and the part of entangled part of her system, she performs some joint quantum operation and send the classical information that what she has done, and depending on that, Bob applies some unitary operation on his part of this entangled photon, and finally the same unknown state destroyed here and reappeared. But note here again, no faster than communication is possible in this process, because Alice has to send some classical information to Bob. Only then this state will be prepared here. And more importantly, after whole protocol, the state will remain unknown to Bob. But what we have done, we have unknown state, we destroy here and reproduce here. This is the quantum teleportation. And this is the space-time diagram for this teleportation protocol. And this is the reference of this paper. This is the Bennett, Brassard, and all their collaborators. So this is now, I think, nearly 15,000 cited paper. It is one of the most prominent results in quantum information theory. Now, how good this teleportation process is? Okay. So that we can quantify if the process channel is not perfect, that we can quantify some entropic quantity. It's called coherent information. But problem is, this is very difficult in general to find because there is some regularization, limit n tends to infinity. Why this is regularization is very difficult? Let us try to explain that. So let us consider some channel and it has some quantum capacity. Some channel epsilon, some channel n1, and this is some encoding process and decoding process, and we obtain some quantum. After this, we obtain some quantity, quantum information, which is this qn. You don't have to worry about for the time being this mathematical expression. So, but we obtain this quantum capacity, and we find that this quantum capacity is 0. We have a second channel n2 for which also this quantum capacity is 0. Now, in our classical world, what it tells, if we have, so through this N1 channel, we cannot send any classical information. Through this N2 channel also, we cannot send any classical information if they are classical channel. Now, I give this both channels simultaneously. Can you send some information? Classical theory says, no, we cannot send any information because classical capacity or mutual information is additive quantity. That's why their capacity will be 0. But in quantum world, very peculiar things happen. So, Q of N1 is equal to 0, Q of N2 is equal to 0, but as a whole, they have a non-zero quantum capacity. So, quantum communication with zero capacity channel. So, this is one of the very famous work in this quantum communication theory, which is by Smith and Leard. And Jonathan Oppenheim actually very beautifully explained this super additive phenomena. It's called quantum blindsight. You appear to be blind in your left eye and blind in your right eye. Why you can see with both eyes, it's beyond me. It's beyond me means our classical intuition cannot explain this fact, but in quantum world, it happens. Similarly, the other capacities, private capacities, it also shows some non-additive, super additivity phenomena. These are example of this is definition of this private capacity. Don't worry about this definition, mathematical definition, and this is example of channel. Also, you don't, for the time being, don't have to worry about this example. The fact you think is that this kind of phenomena doesn't happen in classical world. Okay, now super additivity of classical capacity. When we consider the classical capacity of a quantum channel, then we have to be very careful. We can define classical capacity in different way. Means there are many uses of this channel, and among this input, whether we are using entanglement among this input, and during this decode, whether we are using some entanglement measurement, there are different kind of capacity can define. It's called product capacity, entangled input product decode, measurement capacity, and which is also called Shannon capacity, and then PE means product input and entangled decoding, that is called Holevo capacity, and finally is this entanglement input and entanglement output. And in 2009, Asst actually established that these inequalities are strict, means there exists channel for which this ultimate capacity will be strictly greater than Holevo capacity, which in other sense establish the super additivity of classical capacity. So, okay, at this point, I want to say something regarding this foundational status of this super additivity. Now, you see, classical state, as I was telling, we can think classical state, if it is a deterministic thing, it is a point in phase space, otherwise, it is a probability distribution on the phase space. Or it is a partition function. So, the system is actually in some physical phase space point, but we don't know. We have some ignorance about it. So this is called epistemic interpretation. So similarly, people, means at least Einstein in 1935, his paper, he used to think that this quantum state, this is also something like epistemic. Means underlying this quantum state, some theory is there which is deterministic in nature, and this quantum probability is arising due to our ignorance kind of things. Maybe we don't know the theory at that time, but If we try, we can come up with such a theory. But very recently, people have proved that this quantum theory, quantum state is not this kind of things. Means you cannot give the classical ignorance kind of interpretation for this quantum probability. So, and furthermore, one of my strong intuition is that if quantum state is epistemic, that it should not, then it should not exhibit the super additivity phenomena, because classical variable, classical X variable, they are epistemic, and in that case Shannon quantity becomes additive. In this case they are not become additive, means it is a signature of this non-epistemic nature on Shiontic nature. It's called Shiontic nature of this wave function. However, I have to be careful that I haven't come up with any rigorous proof of this intuition, but this is I'm telling about my intuition. Okay. So far what we have seen, that study of quantum communication model is much richer than its classical quantum. It is exciting that quantum channel capacities, all these capacities, classical, private or quantum, exhibit super additivity phenomena, means something zero channels, from them we can get something non-zero. Means 0 plus 0 can be non-zero if you consider quantum capacities or classical capacities or their private capacities. However, it has also frustrating issues. Why? In most of the case, it is very difficult in general to come up with a single letter expression for these capacities. It is very difficult. Only for few channels we know this exact capacity formula. But we can take it as our challenge for future research, how to come up with this capacity formula for different kind of channel. Okay, so, but now I'll try to discuss some new twist in this communication model. So far, we have considered, let us consider this kind of scenario. So there is some sender Alice and then Bob, receiver, and in between there is two noisy channels, lambda 1 and lambda 2. Now this information first travels through this noisy region and then it travels through this second noisy region. It may happen this information first travels through lambda 2 and then lambda 1 and then it reaches to Bob. So it first travels to lambda 2 and then it travels to lambda 1 and then it reaches to Bob. So these are two possibilities. But in quantum world, more peculiar things we can do. What we can do? There is some control system. If the control system is 0, the information passes through this kind of things. And if the control system is in 1K state, then this information travels through this line. Now we can make this 0 and control system superposed, means which process is happening earlier and which process is later, that concept will become indefinite. You cannot tell it. Like superposition. If it is 0 plus 1 by root 2, you cannot say that system is on 0 state or system is on 1 state. System is simultaneously on 0 and 1 state. It is very peculiar. Similar things we are doing now in the causal order. It is not the causal past of lambda 1 is not in the causal past of lambda 2. In this picture, lambda 1 is in the causal past of lambda 2. In this picture, lambda 2 is in the causal past of lambda 1. But in quantum world, we can peculiarly combine them in such a way this causal relation becomes indefinite. So this causal relation becomes indefinite. Now this particular phenomena, it's called quantum switch, and Guido Chirivella is a scientist from Oxford and Hong Kong. He introduced this concept, and this is the mathematical formulation how to do it, the corresponding Krauss representation, all these things. But we don't need to go into details. And for this qubit Pauli channel, what will be this expression of this quantum switch? That we have written here. Now, what we have shown, we have take one example of Pauli channel, and this particular channel has 0 quantum capacity. It can be shown that this channel has 0 quantum capacity. But we put this channel in quantum switch, means two such channel. So we have this channel 0. I am using this channel consecutively, if I use two zero capacity channel, their capacity means quantum capacity will remain zero. But we put these two channel into quantum switch, and we find that its quantum capacity becomes perfect. No, that means in previously we have seen 0 plus 0 can be non-zero, but here we are trying to establish 0 plus 0 can be perfect. We called it this perfect enhancement. Enables perfect quantum communication with zero capacity channel. And furthermore, some technical theorem we have proved in that paper, that this example is the only example. You cannot come up with no other example. Whatever example you come up with, that example will match with this particular case. Okay. So this is the communication model we are considering, introduced by this scientist. And one fundamental things we proved there, that we say superposition, this indefinite causal order shows superposition in time. So we already, so far we know superposition in space. Means different path, we can take superposition of this path. We have established proof that if we take this superposition of different path, then that cannot give you perfect enhancement. Using superposition of path, you cannot obtain perfect quantum communication if the channels are noisy. So our observation established a fundamental difference between superposition in paths and superposition in times, or in other words, superposition of orders. Okay. So then, so this work actually we have done in collaboration with this Chirivella, and then Chirivella actually put another work where he formulated the rigorous resource theory of communication with superposition of quantum processes. Okay, this formulation particularly, so there are some technical part at this point. This formulation makes a clear-cut separation between internal and external degrees of freedom. So there are some concepts, internal and external degrees of freedom. What we have established, this theorem has been established that if you cannot, that there should be some clear-cut separation between this internal and external degrees of freedom. Only then this theorem can be established. And that's why another group of scientists, Czeslaw Bruckner, he criticized our work. Then we are presently trying to come up with a new theorem which establishes the same theorem, same result, without this kind of perfect distinction. That will put a more powerful result, that superposition in time and superposition in path is fundamentally different. Okay. So this is a task. So this is ongoing. This is a particular task. It's called random. Some technical name is there. Random receiver quantum communication task. This is also a task we are particularly doing in collaboration with Som Shankar. He is a postdoc fellow at Hong Kong University, and one of my students. I'm co-guiding him. He's a PhD student in Essenbos Center. Tomal, he is one of my junior collaborators from Indian Statistical Institute, and Guido Chirivella, he is from Oxford University. So this is, we have done this work. Very soon we will put it on our guide. So far I have discussed this theoretical result. One can ask, what is the experimental achievement? Quantum teleportation, it has been experimentally achieved in 2004. Quantum key distribution achieved in 2007, and quantum supertransferring 2008. Another communication task. I haven't discussed this in detail. I haven't discussed it, but some quantum communication task. This is also not possible in classical world. Now look into that quantum teleportation across Danube. So Danube is a river. So their lab was two labs. One lab is one side of Danube river. Another lab is another side. So they have teleport the quantum system from one side to another side. Means you can consider few kimis, 1.5 kimis. Now very recently there is some experiment that quantum teleportation, satellite-based entanglement distribution. This is also quantum teleportation actually over 1200 kilometers. So one lab is, in this experiment, one lab was at Beijing and another lab was in Vienna. So quantum communication, these are not folk story anymore. We have already, scientists have already established this quantum line more than 1200 kilometers. So if we have few such labs, we can cover the whole world through quantum communication. And more recently, entanglements, this secure communication has been established also by same group of experimentalists. And also another, this is the experimental realization of our quantum enhancement task that we have discussed. Chivela is also one co-author in this experiment. It got published in 2020 in PRL. So that's all. I think we can have some discussion if you have some question. Yeah. If you have some question, please ask it. Ask the question.
Sir, I have a question, sir.
Please.
So, sir, this super additivity, does it
Yes.
imply that our nature cannot be probabilistic, or
No. Super additivity does. This is our nature is intrinsically probabilistic. That is a quantum phenomenon. Entanglement, it is a quantum phenomena. Using this peculiar phenomena, we obtain this super additivity phenomena. Super additivity phenomena you cannot observe in classical communication theory, because this Shannon capacity, mutual information, it can be shown using rigorous mathematics that it is additive quantity.
sir, so you said that it has something to do with that our universe cannot be deterministic, right? In the presentation.
Oh, this scientific nature. Yes, what I said is you see, now probability also appears in classical physics, also in statistical physics. But that probability has some interpretation, that it is our ignorance. We doesn't know, that's why it is probabilistic. But quantum probability, whether that probability also like that, it is an ignorance interpretation, it is not possible. This statement I make, that this particular quantum probability, it is not an ignorance kind of interpretation. Kolmogorov ignorance kind of interpretation we cannot give for this quantum probability. And people have, in a different way, not from the super additivity phenomena, in a different way, people already established that quantum probabilistic nature, you cannot give the ignorance interpretation. My intuition, I say very carefully that it is my intuition. I haven't seen any rigorous proof. I am also trying to prove that this superadditivity phenomena is actually establishing this, what result scientist has proved in a different way. That's what I'm trying to say.
Okay, so that's what I was asking. So basically,
yes.
Right now we don't have a proof that this is just ignorance, right?
No, some different proof is there, but from this communication perspective, we haven't. Some different proof is there. A different kind of proof is already there, but it is not connecting with this communication scenario. Yeah.
Okay, sir.
Sir.
Yes, please.
Sir. So actually, I was. Is there some sort of quantum gates that go in, as in when we talk about the channel, or it is, or is it analogy in terms of analogy? It can be built up using gates or something. In terms of do we have something to do with computation here?
Exactly. Quantum gate is what? Quantum gate is nothing but a unitary process. You see how we define
unitary
this channel?
transformation, yeah.
Yes. Now, what is a channel? Channel is a completely positive CPTP map, completely positive, takes some mathematical operation. But as I say, you can always think it as a unitary on some bigger system, larger system. So quantum process, quantum Channel is nothing but a unitary operation. But you don't have the access of this full system. Environment, you don't have this access. You have only access on the system part. On this system part, it is some CPTP map. That's all.
Okay, so sir, we have then error correcting codes as well in this.
Yes, error correcting code is
For
there. So
communication.
Yes, actually, this when we calculate. Yeah, let me. I understand. I got your things. When we are interested in channel capacity, error correcting code gives us some only bound, but in quantum capacity we can something achieve more. Error correcting code cannot capture everything in this quantum channel capacity. It captures some portion of these things, but not all. But again, these are much more technical things. If you are interested, we can have more rigor. It requires lots of more mathematics. Then we can have. You will understand that error correction scheme gives some particular aspects of this channel, but it cannot capture all. Channel capacity is much more general things.
Okay, sir.
Yeah.
And sir, one more thing that sir, as in if like essentially if I talk about these unitary transformations and stuff, so sir, as essentially a gate, a unitary transformation. So sir, do I have notion of fault tolerance in communication as well?
So fault tolerance is one kind of fault tolerance is also one kind of error correcting code. It is one kind of.
Okay.
Yeah.
I kind of sir. I get that. I get the thing. Thank you.
Any other question?
Sir, I have one question.
Yes, please go.
Sir, at the end of the presentation, you showed that there was recently some experiment was done in quantum communication. What exactly was sent in this experiment?
These particular things.
What was the communication which was done?
No, what I am saying this in this experimental, you see, experimental details. Truly speaking, I am unable to explain. But what this experiment established, this particular phenomenon. In that experiment, they have taken a quantum channel which has zero capacity. So consecutive use of this quantum channel will give you zero quantum capacity channel, but they have superposed it in quantum switch. The superposition that is called quantum switch. The name is given by Chirivella. In this quantum switch, after this quantum switch, the resulting communication capacity, quantum capacity becomes 1. In experiment, of course, you will not get 1. You will get very close value to 1. Means 0.90% success or 95% like that. So what I am trying to say, this is not only theoretically established, but has been established in this experiment also, and this is photonic device. So in principle, it is a tabletop experiment. But what is the experimental details? That I don't know, because all these source they are request single photon source, lots of things are involved. But what I am trying to see, that theoretical prediction, what our result established, that has been empirically established in this work.
Hello, sir. I have a question.
Yes, please.
Hello, sir.
Yes,
Sir, you have told that we can't do communication faster than light, but there's something where he's saying from some special theory of relativity. But sir, the state but the state has already generated over there. So I said there is some linear somewhere at some x distance. and
Yes.
that X is greater than C,
Yes.
and so definitely it will take more than 1 second time for light to travel there, right? So if
Yes.
say, oh yeah, I have said someone that I'll exactly send my do my task at exactly 5.1 seconds, and you have to check
Yes.
it at exactly 5.2 seconds. So
Yes.
at that same time, we are now if we breaking that like we are breaking that law that
Let me
your information
let
can't
me
travel
explain.
faster.
Let me explain, Shubham. Let's say I am here. I am with one entangled particle part, and you are at alpha Centauri. So any light from here to alpha Centauri to reach there, it requires 3.4 year or something like that. Now, if I do something on my entangled part, something will happen at your end, at your part. That is okay. That is completely sure. But that something is very peculiar. Using that something, you cannot send any information. That is very peculiarity of quantum theory. Because quantum theory is probabilistic in nature. This intrinsic probabilistic nature doesn't allow you to take same faster than light information. And look into quantum information, quantum teleportation task. Alice, she has some unknown particle. Let's say Alice is at Earth. Alice has an unknown particle, and the part of her part of this entangled part or entangled particle. And Bob, who is sitting at Bob's alpha Centauri. So Alice do something. Some change has happened at Bob particle, but Bob still doesn't know anything on it. Now, what Alice obtained in her lab, that information she has to send to Bob through some classical channel, classical information. Now, this classical information, it requires again 3.4 years to reach at Bob's end. Only then Bob will do some action on his part, and then the state which has been destroyed at Alice's lab will regenerate it as at Bob's location. This is the quantum teleportation protocol. That's why I am telling in using quantum teleportation, you cannot send faster than light information. But some peculiarity is possible that we are using, that like super additivity of classical capacity. For that, entanglement is required. In the input part, you require this entangled encoding. Only then you can have superadditivity phenomena, classical capacity of quantum channel. This superadditivity phenomena will only obtain using this entangles. So entangle has some peculiarity, but it doesn't have that much power that it will send faster than light communication. It is not possible.
Thank you, sir.
Okay. Any other question?
Sir,
Yes, please.
is quantum teleportation already done several times, or is it still possible in principle only? Means just for information.
Yeah, that's I was telling. So quantum teleportation, as I was saying, the first quantum teleportation experiment was in, this is experimental result, 2004. This Ursin et al. Ursin is, I think he was postdoc student of Anton Geilinger at that time. This is a Geilinger group paper. And quantum teleportation, this has
Oh,
been
sir, I
experimental.
got disconnected. I got disconnected that time.
Okay, okay. So this has been done experimentally, but at that time it was 1.5 km apart. Now presently it has been achieved more than 1200 km. Okay.
Okay.
Sir, I have one question.
Sure, please ask.
Yes, sir. Sir, I heard that this quantum entanglement thing is an instantaneous thing. Like, I heard about this that if we suppose I'm sitting in India and someone
Yes,
sitting in America,
yes,
suppose we interacted at some point of time and then we have no interaction now. Suppose
yes,
it may happen that if we switch on a light over here, something would have happened there also. Like,
Yeah, that is true. That something will happen. But
yeah.
using that something, you cannot send any information. That is the peculiarity. That something, how big scientists try to explain that something, Schrodinger say, okay, there is something steering is happening. Now he introduced the term steering. That okay, I am doing something in my entanglement part, and some change is happening at my friend who is sitting at America. But that something is, that's why I am saying that something is peculiar. That something is not so powerful that you can use it to send information instantaneously. But we can do some other task. That's this quantum information theory try to find out those tasks. So quantum superlativity of phenomena is one this kind of peculiarity where this entanglement gives you this power. But if somebody tells you that using quantum entanglement we can send faster than light information, you can take it from me for the time being that it is wrong, you cannot do it. And after, if you go through in rigorous derivation or this kind of things, you will find it is not at all possible. We can prove actually that using entanglement, quantum entanglement, you cannot send faster than light information. But something we can do, that is true, that's something is not faster than light information.
Okay, sir.
Yes.
Thank you.
Okay, thank you everybody, and please stay safe at home. It's a very hard time.
Thank you, sir.
Okay, welcome.